Formation of a solution is an equilibrium process. We've talked about equilibrium in terms of evaporation, the picture of the Erlenmeyer flask, and we had things evaporating and condensing back in, and we talked about vapor pressure. Same concept here, but the processes are dissolving and crystallizing. So when you put the solute into the solvent, initially the rate of dissolution or dissolving is higher than the rate of recrystallizing. There's a picture here. Because at first there's nothing in solution to recrystallize, but here you have your sodium chloride crystal, and so some of that's going to dissolve. As the concentration of dissolved solute increases, then the rate of recrystallization increases. And that will continue to change until we get a dynamic equilibrium where the rate of dissolving and the rate of recrystallizing are equal. So that's illustrated here. As the solution becomes more concentrated in the sodium chloride that's dissolving, recrystallization is occurring also. And the more sodium chloride that's in the water, the higher the rate of recrystallization. And so at equilibrium, the rate of dissolution and recrystallization will be equal. So if you have a beaker of saturated sodium chloride, you've stirred it up, nothing more will dissolve, and there's some sodium chloride sitting on the bottom. You could sit there and watch it, and you're not really going to see anything happening. But it is changing. There are sodium and chloride ions that are dissolving and going off into solution, and there are others that are coming back and becoming part of the crystals. And what happens if you leave a solution like that long enough, depending on the compound, it could take a really super long time, way more than anybody has patience for. You can actually cause large crystals to grow from really small ones. It's pretty cool when that happens. So any questions about that? So we talk about saturated and unsaturated solution. Saturated means it's full. Saturated solution is one where the dissolved solute is in dynamic equilibrium with the solid solute. If you add more solute to this situation, to this solution, it will not dissolve. It will just sit on the bottom because there's already as much dissolved as can dissolve. An unsaturated solution is not yet saturated, and so it has less than that equilibrium amount of solute. If you add more, it will dissolve. Okay? And then we have supersaturated solutions, which contain more than the equilibrium amount of solute. Right? Does that seem impossible? How can you have more than what is allowed?
Chemistry.
It's chemistry. It's magic. It's magic. You kind of have to fool the solution. It's a little bit like that supercooled sodium thiosulfate that we had in lab last week. The way you form a supersaturated solution is generally by heating a solution and causing it to be saturated or almost saturated at an elevated temperature, and then cooling it slowly without disturbing it. It's a little bit like that cartoon character, that runs off the cliff, doesn't fall till you point out, or he recognizes, oh wait, I'm standing on thin air, and then he falls, right? So the supersaturated solution is, Bugs Bunny off the cliff. If we tell him that he's off the cliff by putting a stirring rod in there, by dropping in a seed crystal, by bumping the test tube, then all of the excess precipitates out and returns to a saturated solution. So supersaturated solutions are unstable, and the excess solute will normally precipitate. So we're going to watch a couple videos about this. Oops, not the desired result. Try that. There we go. not really any words to this, any audio. So this is supersaturated sodium acetate. And that's just a metal rod. Is that cool or what? Those are crystals forming because there's too much dissolved. Putting that rod in there told it, hey, you shouldn't be able to do this. And I'm like, oh, I guess I can't. That's pretty cool. This one's fun too. Well, it just keeps growing. So those are just toothpicks. And see that temperature? 52 degrees. It was at room temperature before. It's sometimes called hot ice because it's freezing, but it's getting warm. You stick the thermometer in there, you stick your finger in there. And it's like almost solid. It's not actually frozen though, it's just precipitating. Let's make sandcastles. Sodium acetate castles. And then it'll just travel up into the beaker. Yeah. We can do something with supersaturated sodium acetate. I don't know that we can do that.
She's just touching it?
Mm-hmm. Just touch it with your finger. So when you touch it, it gives it a nucleation site, a place to start making the crystal. And once that happens, then it goes. Keeps making crystals. Yes. What causes it to what? Well, in order for crystals to form, there needs to be a nucleation site, a place for them to start forming. And so your finger has a surface, your fingerprints and stuff, there's a roughness there. A smooth beaker will not have really any nucleation sites. Now, if you use a beaker that people have stirred with a glass stirring rod too vigorously and it's all scratched up at the bottom, you're probably going to have a hard time making a supersaturated solution in there because all of those scratches in the bottom provide nucleation sites for the crystals to form.
I think that's how rock candy is made, using a supersaturated.
You do use elevated temperature of a saturated solution at an elevated temperature. It's actually a recrystallization type of process. As we saw with this video, that precipitation happens very quickly, right? So what you want when you're making rock candy, which is over here, what you want with rock candy is you want to cool it slowly. You don't actually want it to be supersaturated. You want those crystals to form slowly as the temperature comes down so that you can get nice big crystals. And that has to do with this graph. The temperature of solids, most solids, in water, the solubility of most solids in water increases with increasing temperature. So if you heat a solution of potassium nitrate, here around room temperature, it's 30-ish, 30-something, 35. grams of solute in 100 grams of water. You heat it up to 50 degrees, and now you can dissolve about 90 grams of solute. So with the rock candy, sugar also has a pattern like this, where it's more soluble at higher temperatures. And so you form a solution that's saturated at an elevated temperature. As you cool it down slowly, it will precipitate out. Not all substances increase their solubility, though. Sodium sulfate is one that actually decreases the solubility as you increase it, but that's weird. Sodium chloride does not change much with temperature. It's pretty flat compared to the rest of those. So recrystallization is a technique used to purify solids. You make a saturated solution at high temperature, you let it cool down slowly. As it forms those crystals, it wants to have the lowest potential energy, and the lowest potential energy is when things line up in whatever cubic or whatever crystal unit lattice it's going to form. If everything is perfect, the energy will be lower. So what will happen is it's recrystallizing. That's an equilibrium process. And so you have, say, sugar molecules crystallizing, but you also have sugar molecules dissolving. And the things that dissolve are the ones that aren't in the right place. They didn't match up right, or you may have some impurities that are getting stuck in there, and those will tend to dissolve and not come back. And so you can get more pure crystals by recrystallizing. This is something you can certainly try at home. I would encourage you to look up instructions on how to do it. I remember trying it as a kid. We didn't have the internet then, and so I just, sugar water with a string in it. It just got nasty and got thrown away after a while. It didn't work.
Ours was I did as a kid, the whole entire glass solidified.
Yeah, so you could have that happen where you just get this really hard to clean up jar full of wet sugar, basically, and it's a big old lump. And so that's why you really want to look it up and find out, okay, well, how saturated, how warm should it be, etc. Were you? Were you successful in it? Yeah. So maybe you could ask. Yeah. Yeah, it's really neat. You make beautiful crystals, and it's. We say it's non-toxic, but too much sugar is bad for you too. Chocolate geodes? No, but that sounds fun.
If you have a Facebook, look up chocolate geodes. They're like forming rock candy inside of a chocolate shell.
Nice.
So they crack them open. They're like this big. They crack them open.
It looks like a geode.
Beautiful.
Wow, I'll have to check that out. Chocolate geodes on Facebook.
Or on YouTube,
Probably. Or Google.
Yeah.
Okay, so that was solids in water. Let's look at the factors that affect the solubility of gases in water. And solutions of gases in water are common. The water that comes out of our tap has gases dissolved in it. Temperature has the opposite effect on the solubility of gases. As you increase the temperature, the solubility of gases in a liquid decreases. And we observe this with soda. Warm soda is going to go flat faster than cold soda. What makes soda is that it's got carbonation in it. It's got carbon dioxide dissolved in the liquid. When the carbon dioxide all leaves, then there's no more bubbles. So you could try this at home too, although it's a waste of perfectly good soda. 2 glasses of soda, put one in the fridge, leave one on the counter. Come back a few hours later and taste them. The one on the counter is going to be flatter, if not completely flat, than the one you store in the refrigerator. Even though the one in the fridge wasn't covered or anything, just being cool will keep the carbonation in it longer. You see that when you pour soda. So a 2-liter bottle of Coca-Cola or something, you pour it. If it's cold, there will be some foam, fizzing, but if it's warm, there'll be a lot more. So if you don't want a big head of bubbles on your soda, chill it first, and it'll come out better. The pressure of a gas also affects the solubility of the gas in the liquid. And we see this again with soda. A can of soda is going to have a small space above the soda that is carbon dioxide under pressure. When you release the can and it makes that awesome psst sound, right? That's the sound of the carbon dioxide escaping. And that's the point at which carbon dioxide begins to come out of solution. And as long as the container is open, it will continue to do that. So the solubility of the CO2 decreases. The reason you see the bubbles forming, you can do this in a clear bottle of soda, like a 2-liter bottle that's clear, so you can see into it. When you open it, you'll immediately see small bubbles starting to form. The release of that pressure reduces the solubility of the CO2, and it immediately starts coming out of solution. So here we have a solution of CO2 and water at equilibrium. The rate of CO2 molecules dissolving in the water and the rate of CO2 molecules escaping into the gas phase is the same. So there's movement here, it's dynamic, but the concentration of CO2 in the liquid and the vapor pressure up here, the pressure of the CO2 are going to be constant. If we push down on this plunger and make this space smaller, that increases the pressure of the CO2. You can also think of that as increasing the concentration of the gas. There are more gas, well, it's the same number of gas molecules now, but in a smaller volume. That's going to increase the rate at which the CO2 dissolves and will force CO2 into the water. That's what's going on with the pressurized can of soda. Because it's got CO2 pressure above the liquid, it forces CO2 into the soda. Eventually you'll get to a new equilibrium where the concentration of CO2, the gas in the water, is higher. So the concentration of gas in the water is related to the pressure, the partial pressure of that particular gas. If you just increase the pressure by maybe blowing nitrogen in there, it's not going to increase the solubility of the CO2. They used to sell these things on TV that you could put on your soda bottle and you'd pump it and it would pressurize the inside of the bottle by putting air in it. Well, the composition of air is about 0.6% CO2. So it doesn't really increase the amount of CO2 in the soda at all. It's pretty worthless.
It's a
Scam. You know, it's one of those things where the basic idea was nice, but they missed the chemical detail. It's got to be CO2. Now, if you rig up your airsoft gun or something and put CO2 in there, that will increase the CO2 content in your soda. A safer thing would just be to buy a soda stream, right? And that's all rigged up specifically for carbonating water. Any questions? So of course we need to quantitate this, right? Because we make math, put math in here anytime we can, right? Of course we do. Henry's law gives us the relationship between gas solubility and the partial pressure of that gas. So the equation's pretty simple. The solubility of the gas, which is usually measured in moles per liter, is equal to a constant, it's called the Henry's law constant, times the partial pressure of the gas, which is usually in atmospheres. Henry's law constant depends on the gas, the solvent, and the temperature. So you're going to have to look this up and hope that you can find the values for the particular thing you're looking at. So this table is giving Henry's law constants for some different gases dissolved in water at 25 degrees Celsius. If you're using a different solvent at a different temperature, you're going to need different constants. But these are the constants. Yes?
You would give us that constant.
I would, yes. I don't remember these. You shouldn't remember them. Okay, so we're going to need this one on the next page. The Henry's law constant for water, oxygen and water at 25 is 1.3 times 10 to the minus third molarity per atmosphere. 1.3 times 10 to the minus third. .3 times 10 to the minus third. And that's molarity per atmosphere. So the question says, determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. Well, this is a Henry's law problem. So the solubility of oxygen equals the Henry's law constant for the oxygen times the partial pressure of the oxygen. We look up the Henry's law constant in a table, and then we need the partial pressure of oxygen. That's 0.21 atmospheres. So this is going to equal 1.3 times 10 to the minus third molarity per atmosphere times the partial pressure, 0.21 atmospheres. The unit atmospheres cancels out. My calculator is giving me 0.000273. The unit there would be molarity, moles per liter. How many sig figs should it have? 2. So that would be at the 7, so we could round this 0.00027 molar, or we could put it in scientific notation, 2.7 times 10 to the minus 4 moles per liter. Any questions?
We can just ignore the 25 degrees Celsius and
Well, we can't really ignore the 25 degrees Celsius. That was put in there to let us know that we could use the table on the previous slide.
And the one.
So this one.
Same thing.
The 1 ATM, if it just gave you 1 atmosphere and didn't give you this little hint here, then you'd have to go looking back and find, what's the percent oxygen in air? It's 21%. So then 21% of 1 atmosphere, 0.21, that's the partial pressure of the oxygen. So the problem could be made more difficult. I don't know if I'm going to do that to you or not. I'm worried about what's happening the rest of today. I've been thinking about tomorrow a little bit, but this is, that's like over a week away. No, I won't. The temperature of water is important for aquatic life, for fish, right? Because fish breathe the oxygen that's dissolved in the water. If you increase the temperature of the water, what happens to the amount of oxygen in it? It goes down. And then the fish have a hard time breathing. So you can have thermal pollution of rivers. We've all seen pictures of, factories dumping polluted water into a river. That's bad. But if a company is dumping hot, perfectly pure, clean water into a river, that's also going to kill some things. Because in the area where that temperature is elevated, the oxygen levels are too low to support the fish that are accustomed to living there. That's why if you're trying to keep fish in an aquarium in your home, you need to know what their optimum water temperature is. Tropical fish are accustomed to living in warm water at lower oxygen levels. But cold water fish like goldfish are not going to be happy. Not at all.